Okay, right, we are still on the subject of high voltage, and now we are going to talk of mechanism of breakdown of gases. Now, simply meaning there, I actually don't wanted to do an explanation, but I think moving forward, I think it's very critical, so that's why I'm doing this, okay? Right. So essentially speaking is what is happening there is we are moving, okay, from what I'm going to call low level voltages to high level voltages. A typical example would be, as you will notice here now, we are talking about 110 kV. Kindly note it's a range. What's the upper level of that range? It's 220 kV. Okay. Again, if you look at this, this is what 400 kV. Whoa, that's amazing. But look at this, because this is powerful now. If you move from 400 kV, then at a later stage you'll notice that we are talking about what? We are talking about 800 kV. Now, the moment you start talking about higher, because even here, that's what I'm talking about. Okay, right? That's what 800 kV lines. Okay, so we are moving from low level voltages to high level voltages. Okay, right now, what's the significance of this? Long story short, né? The moment we talk about voltage and current, essentially that speaks to power. So power, it's a product of what? Voltage and current. So let's talk about voltage. Voltage speaks to what? Voltage, né? It is speaking directly to what? Insulator. What type of insulation? That's what voltage is speaking to. Okay, simply meaning the insulation that you use, let's say for 10 kV or 11 kV, it's going to be inherently different from the type of insulation that you use when you are speaking of what? 110 kV. Right. Now let's talk about current. The moment we talk about low current and high current, what does current speak to? Current is speaking to the cross-sectional area of your conductor. Okay? Simply meaning if you want a small cross-sectional area conductor, it means what? Small current. If you want to talk about high currents, now we need to increase the cross-sectional area of the conductor. Okay? So essentially speaking, now being mindful of what I just said, you have to say, okay, so what's the difference between insulation used for 11 kV and insulation used for, let's say, 110 kV? Clearly there's a difference. What is the difference? The difference is the insulation for your 11 kV. At some point, it's going to break down. And we need to understand the point at which it breaks down. Why? So that we can understand its limitations. And essentially speaking, now we are going to delve on what engineers call mechanism of breakdown. In this particular instance, we are going to refer to what? To gases. Because I mean, if you just read this last portion, what does it say? In electrical engineering, all three media. What's media? Media, it's the plural word of the word medium. In your mediums, it's what? Gas, liquid. Think of oil when we say liquid, as well as solids. So in this case, we are going to study the mechanism of breakdown of what? Of gases, meaning gases as an insulator, or as insulation, it has what? It has a breaking point. And in this case, we are going to study the mechanism of that breaking point. Okay, so here goes. At normal temperature, at normal pressure, gas is a what? Excellent insulator. That's good news, because that's what we want. Okay, however, this is now where the trick comes in. The current conduction, simply meaning the capability to conduct current, okay, is of the order of 10 to the power of negative 10 amperes per centimeter squared. All that basically means is the ability of a gas to conduct current. It's very small. Okay? Very small current per unit of surface area, centimeter squared. Okay? Now, this current conduction, simply meaning this ability for current to be conducted, it results from the ionization of air. Now, when we talk about ionization of air, simply meaning the air particles is what? Charged. That's all. Is it positively charged, negatively charged? We don't know. We just need to know that it's charged. Okay, right. So now it says, this ability for current to be conducted, it results from air particles being charged. Charged by what? Charged by cosmic radiation. That's just a fancy way of saying radiation that comes from space. That's it. As well as the radioactive substances present in the atmosphere and the earth. That's it. Now, at higher fields, okay, simply meaning fields are higher. In this case, let's assume it's an electrostatic field. It's an electric, okay, right, let's assume. Yeah? It says charged particles, they may gain sufficient energy. Okay, so let's say your particles are charged. Why would they be charged? They would be charged because they have been introduced to what? To a higher field. And so now they may gain sufficient energy between collisions to cause ionization on impact. Simply meaning they can now cause for particles to be charged. What particles? The end of that sentence, it talks about what? Neutral molecules. That's it. So now it just says at a higher field, charged particles. So simply meaning the particles are charged. Why? Because they were introduced to a higher field. Okay. In this case, let's assume an electrostatic field or some field. Okay, right. Charged particles may gain sufficient energy between collisions to cause ionization. Simply meaning they can now cause neutral molecules to become what? Charged, to cause ionization on impact with neutral molecules. It is known that during an elastic collision, an electron loses a little energy and rapidly builds up its kinetic energy, which is supplied by an external electric field. That's exactly what we just said. I mean, that is the reason why it starts off by saying at higher fields. What fields? What fields are we talking about? At higher fields. What fields are we talking about? At higher fields. I mean, it's right here. At higher fields, charged particles, da 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 da. Right. External electric field. Question answered. Okay. On the other hand, during elastic collision, a large part of the kinetic energy is transformed into potential energy by ionizing the molecule struck. When you ionize a molecule, all it means is the molecule, in this case, we assume it was what? Neutral, and now you have charged it, whether it was positive or negative, it doesn't matter, but now it's charged, struck by the electron. Ionization by electron impact. Simply meaning there's what? Electron impact, and through that impact, what? A charge is now transferred, and that transfer charge is what we talk about when we talk about ionization by electron impact under strong electric field. Is the most important process leading to breakdown of gases. This is deep stuff. Whew. Deep stuff. At normal temperature and pressure, the gases are excellent insulators. The current conduction is of the order of 10 to the power of negative 10 amperes per meter squared, per centimeter squared. This current conduction results from the ionization of air by the cosmic radiation and the radioactive substances present in the atmosphere and the earth. At higher fields, charged particles may gain sufficient energy between collision to cause ionization on impact with neutral molecules. It is known that during an elastic collision, an electron loses little energy and rapidly builds up its kinetic energy, which is supplied by an external electric field. On the other hand, during elastic collision, a large part of the kinetic energy is transformed into potential energy by ionization, or by ionizing the molecule struck by the electron. Ionization by electron impact under strong electric field is the most important process leading to breakdown of gases.